So continuing on with page 20 in the Unit P packet, we have number 4. A 50-pound weight is hung by a cable so that the two portions of the cable can make angles of 30 and 60 degrees respectively with the horizontal. Find the magnitudes of the forces of tension T1 and T2 in the cables if the resultant force acting on the object is 0. All right, so there's a lot of stuff going on with this, but we do see that we have two vectors here that are representing the amount of tension that's being applied to the object in the positive direction. All right, one of them's T1 and the other's T2. All right, so it's just a question of, well, which one's T1 and which one's T2? They make angles of 30 and 60 degrees with the horizontal respectively, but it doesn't say anything about which one has to be T1 and which one has to be T2, so we could take liberty with that and call this one T1 and this one T2. All right, now there is a horizontal. It's like, what horizontal? You know, this object is suspended from the air, but we can assume a horizontal in a variety of different places. I mean, we have a horizontal here, right? And that horizontal corresponds with the angles that are created by attaching the object with the tethers to, I'm assuming, a ceiling. All right, so now we do have the benefit of parallel line relationships. So I could say that this horizontal line is also consistent with this horizontal line, right? In that, based off of parallel line relationships, if two parallel lines are cut by a transversal, the alternate interior angles are congruent. So that would make this a 30-degree angle. And that would make this one, poor quality highlighting, a 60-degree angle. All right, so let me just smidge over my T1 and T2. I'll just put it on the other side, make it look a little bit better. All right, so then it's hard to see, but we also have an angle that's going in the downward direction here from the horizontal, that new horizontal that we just manufactured, corresponding with that 50-pound weight. All right, and that, you know, that's a 90-degree angle if you're going backwards from the horizontal. You know, if we're assuming that this is 0 degrees, we know that this is the 60-degree angle. That's easy enough. This one, I'll do it in Poiple. This one would be 150. And so if we're going all the way around, you know, we can go back 90, or we can go forwards 270 degrees. All right, the idea is if it's going to be suspended in air, the tension created by T1 and T2 would have to give a resultant that's equal to the tension created by the 50-pound weight. All right, so diagram got really messy really quickly, so let me just kind of strip it down to the base components. All right, so I have my T1 and my T2, if I can draw it. Get some arrowheads on it. Poor quality arrowhead, let me bring it in. All right, it's going to create a resultant I'm going to put that resultant, hopefully it'll be somewhat vertical. I just kind of eyeballed it, so it's a little tricky. And not too terrible, but not perfect. I'm just going to kind of wing it. All right. So this resultant vector, that red for resultant, resultant. We'll call that R. That has to offset that 50-pound weight. All right, so we have to have 50 pounds of tension in the positive direction to account for the 50 pounds of tension in the negative direction. Now, how do we get that? Well, we have T1 and T2. The sum of T1 and T2 will give the resultant. All right. Now, we don't know either of those values. That's part of the fun. So we'll figure those out. But we do know one of them creates a 30-degree angle with the horizontal and the other 60. T1, that 30-degree angle gives us 150 degrees, so we'll keep that in mind. And the T2 has a 60-degree angle. All right, so we're looking at, and I'll write them vertically, the magnitude of T1, the unknown magnitude of T1, times the vector cosine 150, sine of 150, the magnitude of T2, cosine of 60, sine of 60, all nice unit circle measures, is going to have to amount to the value of R. All right, now R would be the magnitude of R. Now that R, the brand new R that I created, all right, now it's kind of tough to see because, again, like I said, the diagram got crazy. That's going in the positive direction, and it has these components. So we're looking at a 90-degree angle. So cosine of 90, sine of 90. All right, because again, that has to balance out the 50 degrees in the negative direction. So if you kind of look at it and say, all right, well, what about that 50 degrees in the negative direction? And I say, well, what about it? All right, so let's take a look. If I say I have 270 degrees, all right, that would be 50, that's my magnitude, 50 pounds, cosine 270, sine of 270. All right, cosine of 270 is 0, sine of 270 is negative 1. All right, that would give me a vector of 0, negative 50. All right, so that would be the vector going in the downward direction. All right, if you want, you can call that negative R. All right, so then the big question would be, well, what does that give us here? Well, take a look at what we have. The cosine of 90 is 0. The sine of 90 is equal to 1. I need this to be the exact opposite, but it will be, because if I use the magnitude of R of 50, replace that magnitude of R with a 50, and then run it through using the distributive property or process, I would get 0, 50 as my new vector. Same length, opposite direction. Mission accomplished. All right. So it was just a matter of, once we identify the angle, it would be a matter of applying the appropriate magnitude, which would be 50 pounds. We have to account for 50 pounds. Once we do that, we're off and running. All right. So back to this, we're looking at magnitude of T1 multiplied by the cosine of 150. Now, cosine of 150 is going to be its 30-degree reference angle in the second quadrant. All right, so that the cosine of 30 is equal to radical 3 over 2, but it's negative because it's in the second quadrant. So radical 3 over 2, T1, all right, plus T2 multiplied by the cosine of 60, which is 1/2. And that whole thing is going to be equal to the cosine of 90 multiplied by its corresponding magnitude, whether it's 50 or otherwise. Cosine of 90 is 0, so that would result in a value of 0. All right, so we're working our way down the line. All right, so T1 cosine 150, T2 cosine of 60, R, all as magnitudes, cosine of 90. So then T1 multiplied by the sine of 150, so the second quadrant, is going to be 1/2, 30-degree reference angle, all right, plus T2 multiplied by the sine of 60. Sine of 60 is equal to radical 3 over 2, first quadrant. So radical 3 over 2, and that whole thing is going to be equal to 50. All right. So we're going to solve this system of equations using the calculator where we have T1. I'm going to replace that with an X. And where we have T2, I'm going to replace that with a Y. All right. So it's going to be negative square, well, let me just put the fraction in there. Square root of 3 over 2 x plus 1/2 y is going to be equal to 0. Then we're also looking at 1/2 x plus the square root of 3 over 2. So let me get my fraction in there. Square root of 3 over 2 y. That's going to be equal to 50. All right. So what we're looking for here is the intersection. So tap on that. Tap on it the one time to indicate that there is a point of intersection. Tap on it the second time so it indicates what that intersection is. All right. So that gives us a value for x of 25 pounds. And for y, about 43.3. What do they say? Rounding 2 decimal places, 43.30. So 43.3 really. But I'll say, I said 2 decimal places, I give 2 decimal places. All right. So we have the tension, 25 pounds in one cable, 43 and change in the other, and we're good to go. Now, for those of you who are linear algebra minded, and when we incorporate the third dimension, more and more of you will want to be, so that's a good thing. We can use some techniques that are associated with linear algebra in order to come up with solutions here. So what I'm going to do is I'm going to rewrite this linear combination as a product of a matrix and the vector T1, T2. So I'm going to say negative radical 3 over 2, 1/2, 1/2, positive radical 3 over 2. All right, so that's going to be our matrix, our coefficient matrix, and that's multiplied by vector T1, T2, specifically the magnitudes. And that gives a result through that matrix multiplication of 0, 50, the vector 0, 50. All right. So what does this have to do with anything? Excellent question. Well, there's two ways you can go about solving this. One would be by finding the inverse of this matrix and multiplying it by the given vector, in this case 0, 50. The other way would be to create an augmented matrix. And if these words don't have a whole heck of a lot of meaning to you, that's okay, because it's all linear algebra. But matrix T1, T2 could be thought of as the inverse of this matrix. I'm just going to paste it in there. So this becomes more of kind of a procedural thing for those of you who don't have experience with linear algebra, and it might be kind of an aha moment for those of you who do have some linear algebra experience. Either way, it's going to be okay, because everybody can use this technique. It's just some people are going to understand the why only, and the why and the how, and some people will only understand the how. All right, at least until they take a course on linear algebra or do some follow-up research. Honestly, I don't know that you need to take an entire course on this to understand it. Just you might have to do a little bit more work on your own. All right. So this would be one technique. Now, that's great, all interesting stuff, but how do we get an answer from this? Well, if you go into Desmos, not this part of Desmos. If you go to desmos.com, I'm now logged in. Fantastic. Desmos.com. there's other ways to get there, but no, actually, I do have to expand my page a little bit. I thought there was a drop down, but there isn't. At the bottom of the page is what I meant to say. But if you hit Math Tools, you'll see an option that says Matrix Calculator. So I had to expand in order to get there, but then I can kind of bring it back. So what we do is we put in a new matrix. It's a 2 by 2 square matrix. So I type in this information. All right, so I'm going to put in the fraction. You know, it works the same way as an ordinary Desmos calculator. Negative radical 3 over 2. Then you have the 1/2. You got another 1/2. And then you got the positive radical 3 over 2. All right, so that's matrix A. Lock it in. Then the other part you can, the other vector you can call whatever you want. I'll just say new matrix. It's going to be matrix B. I'll get rid of one of the columns because I want it to be just a 0 and a 50. So 0, 50. And so what I'm going to do is I'm going to take matrix A. So I tap on the A. I'm going to invert it, and then I'm going to multiply it by matrix B. All right, and then it'll give us the result. And so why does this work? Well, there's matrix multiplication, but there's no such thing as matrix division. But we do know an inverse is the opposite operation. Like if you wanted to invert addition, you would subtract. If you wanted to invert multiplication, you would divide normally. But with matrices, there's a specific technique that you'd have to follow in order to come up with the inverse. All right, but by finding the inverse and multiplying it, that's analogous to actually dividing matrices. So we're accomplishing the same thing that you would accomplish if you were to quote unquote divide both sides of an equation by a particular value, if it were an algebra course. So 25, 43.30, those numbers look familiar. That's what we got before when we did it using a graphical technique, right? But this is a matrix approach. There's another matrix approach. Like I said, you can use an augmented matrix. And that would be, again, you know, just a lot of writing more than anything else. But in theory, you wouldn't do a whole heck of a lot of the writing. This would be happening in your head. I'm just doing this so that you know what the heck I'm talking about. And even that could be debatable. So what we're doing, and let me just wipe out all this stuff, is we're creating an augmented matrix that consists of the 2 by 2 square matrix and the result of the linear combination. All right, so we put all that in, and I'm starting from scratch here. So matrix, new matrix, 2 by 3 now. So again, you know, the long journey of typing it all in. Negative radical 3 over 2, 1/2, 0, well 0 is already there, I could have left it, 1/2, radical 3 over 2, oh, let me put the fraction in first, and then 50. All right, so what we can do here is we can row reduce this. So we put it in what's called reduced row echelon form. All right, so that's using what's known as elementary matrix operations in order to simplify a matrix without actually having to show the work. All right, so we select ref, type in the A, it'll simplify it down 1 0 0 1. I don't want to close it up yet, and we still get that 25 and 43.30. It's just, it kind of means something a little bit different now. Right? If you think about what we originally used in order to get it into the matrix, we took the coefficients of T1 and T2 and what the whole expression was equal to. Well, these would be the new coefficients for T1 and T2 and what the whole expression would be equal to. So now I'm saying 1 times T1 plus 0 times T2 is equal to 25. Well, isn't that the same as saying T1 is equal to 25? And for the second row, I'm saying 0 T1 plus 1 T2 is equal to 43.3. Well, isn't that the same as saying T2 is equal to 43.3? Right, so it's another way of going about doing things. And so it's up to you. There is, some additional background information that needs to be in play here in order for you to use either of these matrix techniques. Your linear functions need to, first off, they need to be linear. They need to be in the form of ax plus by is equal to c. But if you have your system in that form, then you can use either of these matrix techniques. For now, you may be fine with the graphical approach, and if